I want you to recall what was discussed in Unit 6, which was how to draw Lewis structures from chemical formulas. And we're going to take that a little bit further in this unit, which is all about molecular geometry, intermolecular forces, and bonding theories, to try to get a better visual of how these molecules look in real life. And in this first video for Unit 7, we are going to discuss VSEPR theory, valence shell, electron pair repulsion theory, and also attribute bond angles to these different shapes. Okay, before diving into this video, you may want to review some Unit 6 concepts. Unit 6 concepts such as typical, bonding of carbon, nitrogen, oxygen, and fluorine. And then also there were a couple of videos on step-by-step instructions how to draw Lewis structures. In this unit, Unit 6, we didn't really discuss the shape of the molecule. We drew the bonds on a flat piece of paper, sort of spaced out evenly, but we never attributed a three-dimensional shape. In here we are, and we're going to use what's called VSEPR theory, which is valence, shell, electron pair repulsion. Okay. And I want us to think of these electron pairs as balloons, and you'll see why shortly. Actually, the cover page, the cover picture, we do see balloons, and these are the general shapes of molecules as you increase the number of bonds, as you can tell from 2 to 3 to 4 to 5 to 6 bonds from a central atom. But we'll get back to that in just a bit. Why don't we look at a particular molecule that we saw in Unit 6. In Unit 6, we saw a molecule BeF2, and that molecule has a beryllium atom in the middle. So beryllium is the central atom, fluorine are the outer atoms, and we complete the octet rule for the outer atoms. You can also double check. Beryllium has a valence of 2, and fluorine has a valence of 7, but we have 2 of them. So 2 times 7, that equals 16. 16 valence electrons total, and with a Lewis structure, you want to see, or you're required to show all the valence electrons as dots electrons, or lines as bonds. 2, 4, 6, 8, 10, 12, 14, 16. You recall this is an example of an incomplete octet, which is fine for these metals like beryllium. It's group 2, right there, group 2. So this is an incomplete octet. But now our concern here in Unit 7 is the shape, based on this valence shell electron pair repulsion theory. Another way to say this is that like charges repel. And if we're looking at the electrons, those electrons are negatively charged. So like charges repel, and the corollary is opposites attract. But here we're talking about repelling, because what is repelling in this molecule are the electron pairs of these bonds. And I did want us to think about these as balloons. And when you hold two balloons, not because of any repulsion, so to speak, but just due to physical bumping into each other. So there's your balloons, and it forms a straight line, linear. And you could do this with actual balloons, and you see here they're linear. We want to maximize the angle between these two electron pairs. So this is our first shape, and we'll call this the molecular geometry. I'm going to talk more about molecular geometry in future videos, but for now, it's a shape made by the atoms. We're going to call that the molecular geometry, and we're interested in angles. Okay, well now we're interested in angles, and that angle is 180 degrees. So we're looking at this axis, the fluorine, beryllium fluorine axis, and that is 180 degrees. And right, this is linear. Okay. All right, let's move on to maybe a central atom that has 3 bonds. Again, we're going to have an incomplete octet. As we go through these examples, in Unit 6 and Unit 7, it might be a good idea to keep a list of chemical formulas and their Lewis structures, and now we can add to that. We could add the molecular geometry, and we could add the bond angle. But what if you have 3 balloons? Okay. So far, what are we calling a balloon? We're calling a balloon a bond, or a bond a balloon. So I'm going to keep a running list because we have other types of balloons. But for a balloon, right now we're thinking of it as a electron pair. And so electron pair or a balloon could be a bond. I'm going to leave some space here because we're going to add more to this. And I'm going to specifically say one balloon. So a bond is one balloon, and this bond is another balloon. Two balloons, when you separate them as far apart as possible, form the linear geometry 180 degrees. Let's take a look at, let's see, boron, and I think, well, boron trichloride, another example. And boron has a valence of 3 plus, so here's boron in the third group, or the 3A group, and chlorine, there's 3 of them, and again 7 electrons. That halogen, 24 electrons. And simply the way we drew it, well, I think actually the way I drew it on Unit 6 videos was I just made everything look like right angles to each other. Again, we weren't concerned about geometry or the shape in Unit 6. We were more concerned about getting the proper, valid Lewis structure. There are 24 electrons, so again, we fulfill the valence count. Again, we have an incomplete octet because boron. So beryllium was group 2, boron is group 3. It's okay to have an incomplete octet for boron. Now take a look at what happens if we're saying a balloon or a bond is equal to 1 balloon. We actually have 3 balloons tied together on the central atom boron. And again, if you go to the picture, 3 balloons is right here. They lowered it, or they flattened it out, because they want to show you that these 3 balloons are in the same plane, and they are separated, in this case, by 120 degrees. Let me show you how we could draw that. So this is fine. Fine drawn for Lewis structure, but if you want to indicate the actual three-dimensional shape, really it forms sort of like a wheel with three spokes. Because again, valence shell electron pair repulsion theory says that these bonds, these electron pairs, got to be separated by as much space as possible, and that would be a 120-degree angle. And the molecular geometry is called trigonal planar. In a video, probably the next one or the second one after this, we're going to go over the shapes. But right now, calling this trigonal planar. And let's see, what else do I want to say? Okay, I think that's it. All of these bond angles are 120 degrees. So that is the ideal bond angle for a trigonal planar molecule. But I also want to look at some deviations, and there are going to be deviations. And a deviation example could be SO2. So SO2 is kind of tricky. It's neutral, or net neutral. And we have a sulfur which has 6 valence electrons plus 2 oxygens that each have 6 valence. That is 18. Okay. Just drawing a Lewis structure, not concerned about shape. We draw the central atom S. Central atom is S because it is the less electronegative atom between sulfur and oxygen. That was one of the guidelines if you're having trouble figuring out what the central atom is. And the trick is to draw your outer atoms and then make them fulfill the octet rule. Okay. Now look at this. Are we short electrons? Because I think we have 2, 4, 6, 8, 10, 12, 14, 16. We're short 2 electrons. And the step was, if you're short electrons after you make all the outer electrons fulfill the octet, those extra electrons that you're missing go on the central atom, and I'll put it as a pair. I'll tell you now that a balloon can also be a lone pair. What does that mean? It means that a lone pair will also repel, and it will repel other electrons in bonds, and other electrons in lone pairs. So again, we're keeping a list. So a bond, a single bond, or it could be a lone pair. So we'll make a balloon for it as well. But now, what about the Lewis structure? This is Unit 6 material, because we're not really done, because, well, sulfur should at least fit the octet rule or have a hypervalency, an expanded octet, some people like to call it. It doesn't even have an octet, 1, 2, 3, 4, 5, 6. Okay? And also we have charges that I think we can get rid of. Right? This is a negative. This is a negative. Oxygen with 1 bond and 3 lone pairs. And sulfur, remember the formula? Formal charge equals valence electrons minus sticks plus balls. That is actually plus 2. So that's not good. It's a 2 plus atom, which you definitely want to try to avoid. I can't think of a valid Lewis structure that has an atom that's plus 2 or minus 2. If it's a charged, it's minus or plus or neutral. So to get rid of that charge, to get rid of these charges, also on the oxygens, why don't we move this lone pair and this lone pair? And the result is this. Again, it may not be a big deal that if you didn't know how to draw the Lewis structure sulfur dioxide. It's not a big deal. It is a big deal if you're not able to reproduce the steps to get to the correct Lewis structure. And this is good. That sulfur actually is neutral, right? It's 6 minus sticks plus balls equals 0. So all the atoms are neutral. Okay? And sulfur has an expanded octet. It's hypervalent. And the oxygens are neutral as well. But what about the balloons? See, I'm also counting a balloon as a lone pair, or a lone pair as a balloon. So here I have 3 balloons. And just from the cartoon or the photograph, you saw that the 3 balloons form a 120-degree angle. Ideally, but I'm running out of space here. But I want to give you something that's going to change that a little bit. And this is something that you can memorize. A lone pair repels bonding electrons stronger. So the repulsion is stronger. Let me write it this way. The lone pair bond repulsion is stronger, or you can even say larger, but we'll say stronger than a bond repulsion. In this case, it's not going to be that big, but there is going to be a difference. And because I'm going to draw it like the balloons. I'll have a lone pair up here, and oxygen to the bottom left, oxygen to the bottom right. Here, fill in your lone pairs, because what am I trying to show? I'm trying to show, and I am going to draw like a little lobe encapsulating the lone pair, because that is we're going to know it as a balloon as well. It repels electrons. Not only is that lone pair a balloon, but when you think of a bond, right? Our bonds were balloons, just like for BEF2. But even if you have a double bond, that is considered as one balloon, and you could use, this teardrop shape to encapsulate both bonds. So it is a total of 4 electrons, but it's still considered one balloon, and it's going to be close to 120 degrees. Before I tell you the real number, let's add to our list. One balloon can be a bond, a lone pair can be one balloon, and even a double bond can be one balloon. Or we don't see an example here yet. I don't think we're going to see an example in this video, but a triple bond is also considered one balloon. So don't get confused because you see 2 bonds here, right? It's not 2 balloons, it's one balloon that encapsulates those 2 bonds. Okay, so where's the climax? The take-home lesson is that since that lone pair repels the bond stronger, it's actually pushing these bonds a little bit closer than they want to be. And we don't have a full 120-degree angle here. We actually have a 119. Not a huge difference. I have some examples where the difference is going to be a much larger deviation, but it's 1 degree off from our ideal 120 degrees. Okay. So far, we've seen an example with 2 balloons. We've seen an example with 3 balloons. And really, the system where you'll see very distinct deviations from ideal is example with 4 balloons. And before I give you those examples, let's go back to the cartoon and let's look at the 4 balloons. So we've done 2 balloons, we've done 3 balloons. Not only have we done 3 balloons with 3 atoms around the central atom, but we saw that we could have 3 balloons with only 2 atoms around the central atom, the SO2 example. This is 4 balloons, and it makes a shape called tetrahedral. And let me show you that example and some deviations. The classic example for a tetrahedral shaped molecule is CH4. We know this as carbon tetrahydride, but organic chemists know this as methane. Not a huge deal, but now I'm going to jump and show you how I like to draw this in 3 dimensions. So not only am I drawing the Lewis structure, I'm indicating some shape. And the shape, might be new for many of you, the shape is going to be indicated with wedges and dashes. Wedge means a bond coming towards us, a dash means a bond going away from us, and here's a model. Okay, so if I hold it like that, you see how the bond to the left is in the plane of the paper, whereas this hydrogen is coming towards us, and now the hydrogen I'm holding is going away from us. The molecular geometry, so the Lewis structure is fine, it's just now we're using wedges and dashes as well to show 3-dimensionality. The molecular geometry is called tetrahedral. We have 4 balloons, and each of those balloons has an atom. Tetrahedral. The bond angle for a tetrahedral molecule, and you could take any hydrogen-carbon-hydrogen bond angle, that's 109.5 degrees. Now, I'm going to draw another molecule that has 4 balloons, but one of the balloons is going to be a lone pair. So I'm going to go through this a little bit fast. By now, you should be pretty comfortable actually drawing the Lewis structures for these simple molecules, the ones that have a central atom and 2, 3, or 4 atoms around it. But the correct Lewis structure for ammonia is this. This is the Lewis structure, and it has the right number of valence electrons. 5 plus 3 times 1 equals 8. Yep, 8. 2, 4, 6, 8. But now, because we know that a lone pair can also count as a balloon, we have 4 balloons. This is 4 balloons, just like methane is 4 balloons. So I'm going to draw it using wedges and dashes, and I'll put the lone pair on this theoretical bond going up, this up direction, and we have H, H, and H. Why did I draw wedges and dashes for these H's? Because I'm just following this example, and here's the model, right there, and I'm taking off this bond. So now I have a nitrogen with 3 bonds, but I like to keep the shape made by the electrons because it does have 4 balloons, and I'm going to encapsulate that lone pair in this loop. Okay. So that's ammonia, and yes, you can think of this as a balloon as well. Because balloon and bonds repel stronger than a bond-bond repulsion, it's going to push, that lone pair is going to push these hydrogens a little bit closer to each other than it wants, or what's ideal. And that bond angle is now not 109.5, but a smaller 107 degrees. So this is where it gets a little bit tricky. The molecular geometry of this is not tetrahedral, because the molecular geometry only looks at the atoms. And I don't want to go through that here. Well, maybe I will. Because what have we been actually basing our angles on? The bond angles were based on shape made by the balloons. Okay? And obviously we're using VSEPR theory, valence shell electron pair propulsion. That shape made by balloons has a special name. It's called electron domain shape. And we'll talk more about electron domain shape in future videos. But yes, the electron domain shape is tetrahedral. But the shape made by the atoms is not tetrahedral because we don't have an atom in this fourth bond going straight up. So when we look at the shape of the molecule, we call it the molecular geometry. It's the molecular geometry here. Again, let's take off this so it doesn't confuse us. It's a shape made by the atoms themselves, not the electron pairs or the balloons. The electron pairs and balloons cause the shape made by the atoms, but we only look at the atoms when we talk about the molecular geometry. This is called trigonal pyramidal. Ammonia is trigonal pyramidal. 4 balloons. Now, what about H2O? This will be our last example. The trend is we're pushing these bonds closer together when we add a lone pair. So water, and I'll draw it like this. Water has 2 lone pairs. Each of those are balloons. But each bond is a balloon as well. So the electron domain shape is still tetrahedral, but the shape made by the atoms is what's called bent. Again, in a future video, we'll get all of this in a table, perhaps, and get it all organized. But right now, we're worried about the angles and deviations. So normally, for 4 balloons, you would expect 109.5 degrees, but because lone pairs push harder away from bonds, hence pushing the bonds closer together, this bond angle is less than 109.5, and it is around 104.5 degrees. If I zoom out, you see how each of these cases, CH4, NH3, and H2O, each have 4 balloons. I'll write it here also, 4 balloons. The ideal bond angle is 109.5, but as we add more lone pairs, we push those bonds closer than they actually want, and we go from 107 and then to 104.5. Okay? So your professor may want you to be that exact. Maybe not exact as 104.5, but at least you should know that it is less than 109.5. And this is less than 107, or sorry, 107 is less than 109.5. Okay. Again, don't worry about these terms. We'll get to those, and we'll look at some other shapes in future videos. But again, we wanted to talk about deviations from ideal bond angles, and the ideal bond angles coming from VSEPR theory.